Hey everyone, and welcome to this explainer. Today, we are heading right to the bleeding edge of quantum computing. If you follow the industry at all, you already know we've entirely moved past the, hey, can we even make quantum mechanics compute phase. We are now staring down the single biggest, most central problem defining the field today, and that is scalability. How on earth do we take a fragile, insanely complex quantum system and scale it up to millions of qubits? We're talking about solving problems that would take today's supercomputers literally millennia to crack, all without the entire system just collapsing into static and noise.
To really tackle that, we've got to ask a fundamental question. What actually makes the perfect qubit? Conceptually, sure. Anything in the universe that can bounce between two well-separated, stable energy states can technically be a qubit. But theoretical physics in a lab is one thing. Mass production is a totally different beast. The real test the industry is sweating over right now is figuring out which of these wild, exotic technologies can actually be manufactured efficiently, consistently, and, most importantly, at a massive scale.
Okay, let's dive into this. When we look at the current battleground of quantum architecture, the sheer variety of technologies fighting for dominance is just fascinating. I mean, we've got major companies and research labs backing atoms, ions, photons, electrons, and even completely manufactured superconducting devices. Literally everyone is desperately searching for that perfect Goldilocks zone, the ideal balance between keeping those high-quality, pristine quantum states and actually having a scalable manufacturing process.
So here is our roadmap for today's tech tour. We're going to cover the qubit scaling race, microwave-free silicon spins, IBM's hybrid hardware vision, the qubit transit system, room temperature diamond qubits, and finally, we'll ask, can these technologies actually scale?
Let's jump into part 1, the qubit scaling race.
Section 2, microwave-free silicon spins.
Now you might be wondering, if there are some architectures out there already boasting thousands of qubits, why are we focusing today on contenders who are working with just a tiny handful? Well, the answer is that these groups are starting small because they are absolutely convinced that their unique foundational physics will ultimately scale way better in the long run. Take HRL Laboratories as a prime example. They recently published this highly publicized paper in Nature detailing a massive breakthrough involving manufactured quantum dots holding single electrons. Let's define our terms real quick. In this context, a quantum dot is basically a manufactured trap. By using electromagnetic interactions in a tiny patch of silicon, they can confine a single solitary electron in a region smaller than its own wavelength. Once it's trapped in there, they can manipulate its spin, up, down, or a superposition of both, so it acts as a qubit. And here's the kicker. Because these dots are built in silicon, they immediately inherit the massive, decades-old scaling advantages of traditional processor manufacturing. We already know exactly how to pack millions of microscopic wires into silicon.
And this brilliantly illustrates the real leap forward. Traditionally, electron spins are notoriously hard to keep stable. They usually have to be controlled by these big, bulky microwave cables feeding directly into absolute zero refrigeration systems. It's a logistical nightmare. But HRL, they just eliminated the microwaves entirely. Instead, they use a sleek 3-dot setup. By just tweaking the standard electronic wiring, they can control how much the spins of 3 adjacent electrons interact with each other. This whole thing relies on the Pauli exclusion principle, which basically dictates that no 2 electrons can have the exact same spin under certain conditions. So by managing these interactions purely electronically, they completely remove those massive engineering headaches and all that bulky microwave cabling. It is incredibly elegant.
And honestly, the results are staggering. HRL's system featured 18 qubits. Their traditional processor controller, which they optimized for low temperatures, consumes less than 3.5 watts. And that's even though it was manufactured on an older, highly accessible 130-nanometer process. But the most important part? They demonstrated a logical error rate of less than 1%. These specs are huge because they prove that HRL's future scaling challenges are now mostly just engineering problems, not physics problems.
Moving right along to Section 3, IBM's hybrid hardware vision. So, shortly after HRL made these massive strides, some seriously industry-shaking news dropped. IBM, a massive player who has traditionally been heavily invested in those bulky superconducting loops known as transmon qubits, went ahead and acquired HRL and their microwave-free tech. Now, why on earth would they buy a technology that totally contrasts with their existing control systems? Well, IBM's director of research, Jay Gambetta, explained it perfectly. He said, "It gives us flexibility to keep both parts going in parallel, build on the same foundation. I want to have the flexibility to build my hardware that maximizes both of them." It's brilliant. IBM's master plan here is to use silicon as the universal base. Eventually, they envision running entirely different types of qubits side by side on the exact same hardware. They could use some for memory and others for creating what are called magic states, which are these complex configurations that are absolutely essential for error correction. It's all about perfectly optimizing the entire system.
Let's move to and see how this builds into Section 4, the qubit transit system.
This brings us to our second major contender in the scaling race, a brilliant research group out of Delft University of Technology. But to really appreciate Delft's breakthrough, we first need to understand the routing problem. See, manufactured qubits have historically been severely limited by static, rigid chip wiring. If you suddenly need to change your error correction geometry, you can't just move things around. You basically have to design and fabricate an entirely new chip from scratch. That is a massive restriction, especially when you compare it to atom-based or ion-based systems where you can literally just freely move qubits around with lasers to connect them.
Well, Delft solved this by literally creating a microscopic transit system for qubits. I'm not kidding, it's like a tiny city grid. Check out these steps. First, they start with an electron in a quantum dot. Then, they actively move that electron spin along a 1.2 micrometer bus route right across the chip. Next, it parks at an unoccupied bus stop, and finally, it entangles with a neighboring spin. By dynamically moving these electron spins around the solid-state chip, they are combining the highly scalable manufacturing of silicon with the incredible dynamic, algorithmic flexibility of atom-based systems. It's a total game-changer.
And the crazy thing is, they're doing this with stunning accuracy. Delft is achieving an incredible 98% fidelity rate when sending a spin from one end of the bus to another and back. Now look, it's not perfect yet, right? Noise that creeps in during the movement and the entanglement exchanges is still a real hurdle that they are actively characterizing and fighting. But the proof of concept for a dynamic, fully scalable quantum chip, it is undeniably here.
Section 5. Room Temperature Diamond Qubits.
Now we introduce our final and, honestly, perhaps most surprising contender, pioneered by a company called Saxon Q. To grasp why this tech is so wild, let's look at the physics for a second. A pure diamond is basically a carbon lattice. It's this regular, perfect array of carbon atoms sharing bonds with all their neighbors. But if you introduce an impurity, specifically a nitrogen atom, something really special happens. Nitrogen naturally forms one less bond than carbon. This creates what's called a nitrogen vacancy, which leaves a neighboring carbon atom with a single, lonely, unbonded electron. And just like with those silicon quantum dots we talked about earlier, the spin of that isolated electron can be manipulated to act as a highly stable qubit.
Now, for a whole decade, the main problem was that we simply couldn't control exactly where these nitrogen vacancies formed. That meant every single diamond chip had to be custom wired and totally bespoke. You just couldn't mass produce it. It couldn't scale. But Saxon Q just revealed a massive engineering breakthrough. They can now actually place these nitrogen vacancies precisely within a 10 nanometer radius. By doing this, they have successfully transformed bespoke, unpredictable diamond chips into standardized, highly reproducible hardware. Now, what's really interesting about this slide is the sheer practicality of what Saxon Q has managed to achieve. It's astounding. Because these are diamond qubits, they operate entirely at room temperature. No supercooling, no massive absolute zero liquid helium refrigeration systems. None of that. The hardware fits right into standard server rack mounts, and it plugs directly into normal power supplies. They've built this modular 8-qubit core design, and get this, they are already selling 100-qubit units that are expected to begin shipping in just a matter of months. This isn't just theoretical anymore, it is happening right now.
Finally, Section 6. Can these technologies scale?
So we've just seen 3 radically different approaches to managing and maintaining qubits. So the crucial point is this. We have HRL and IBM leveraging silicon spins with a logical error rate below 1%. We have Delft University proving that their dynamic qubit bus works with an awesome 98% movement fidelity, and we have Saxon Q pushing diamond vacancies with greater than 99.9% gate fidelity. All 3 of these wildly different methods are actively achieving the incredibly high fidelity required to make fault-tolerant quantum computing a reality.
The physics clearly works across the board, right? The gate fidelity is genuinely excellent for all of them. But that leaves us staring at the ultimate question to wrap up on. Which technology will actually scale? Will the future of quantum belong to standard silicon manufacturing, hybrid dynamic routing, or room temperature diamonds? Make no mistake, the winner of this scaling war won't just dominate a new market. They are literally going to dictate the future of computing itself. Thank you so much for joining me on this explainer, and definitely keep your eyes on the quantum horizon.